All right, let's dive right into finding the power series or the Taylor series for a regular old differentiable function. So for us, what we're going to assume here is that our function f of x has a power series representation. So if we assume this, we're going to be able to write any old function f of x that has a power series representation in the following way. So it implies that our function f of x can be written as that infinite series from n equals 0 to infinity of some coefficient c sub n times x minus a to some power n. This is our assumption. Now this just looks like a standard old vanilla power series for us in a very general sense, and that's exactly what it is. So the first couple terms would be c0 plus c1 times x minus a to the first power plus c2 times x minus a squared, and so on. Okay. And again, this is just rewriting that line above it. So if we're asking ourselves, well, if we have this function f of x, we're assuming it has a power series representation. Let's think about what we know so far. Going into this problem, we would be told what we want a to be, or where we want to center our power series. So going in, we know a. So in your mind for this exercise, you could think about a equaling, say, 0 or a equaling 1, but a is something that we know. We're choosing where to center this power series. Okay. So if we're looking at this above line, again, this f of x just written as this general power series. What we're assuming, of course, is we also know f of x. And what I mean by this is you can think about this as f of x equals, say, like something like sine. We're trying to represent a specific function as a power series here. So we know a, we know f of x. The only unknowns are all those coefficients. So like c0, c1, c2, c3, etc. All those infinite amount of coefficients, those we don't know at that point. So our whole job for Taylor series is figuring out, you know what? How can I figure out the true value of c0, c1, c2, c3 for a particular function f of x centered at a particular a value? So our goal here is for a function f of x we want to find those c values. All right, so now that we've listed our goals, what we know, what we don't know, let's go back and see if we can come up with a recipe for finding C0, C1, C2, C3, and so on. So I'm just going to rewrite what we know from our power series. F of x is equal to some C0 plus C1, x minus a, plus C2, x minus a squared, and so on. So first things first, if we're going to try to find all those c's, let's start in order. So the first thing, let's try to find C0. Well, if we look at that above function, where we have f of x is equal to C0 plus C1 x minus a plus C2 x minus a squared and so on, we know at this point what this function f of x is. If we're going into this, we're thinking f of x is something like sine, it's cosine, it's e to the x. It's some function we're trying to find its power series representation at. So we could presumably evaluate that function at any x value we want. The other thing we know is, we know the value of a. All these a's, we're choosing what a is. We're thinking, hey, for this problem, a equals 0 or a equals 1. But a has some specific value. So if we're trying to just figure out what this C0 value is, we can ask ourselves, what clever value of x could we evaluate f of x at to get C0 by itself? And well, if we're staring at this for a little bit, we might be able to convince ourselves to try, say, x equals a. And let's see what happens when we evaluate f of x at x equals a. And the intuition for doing this is basically if we look above, we see all these terms that are like x minus a squared, x minus a cubed, x minus a to the fourth, and so on. And well, if we evaluate f of x at a, we're going to get a minus a squared, a minus a cubed. All those terms are going to be wiped out. So if we plug in x equals a, we're just evaluating, again, our function f at a. We get C0 plus C1, now a minus a, plus C2, a minus a squared, and so on. In other words, all of these terms higher than the C0 term are going to go to 0 because we're getting a minus a. So what we get is that C0 has to actually equal f evaluated at a. So let's hold on to this. So at this point, we know one coefficient. We know that first coefficient, C0. And what we're hoping to do now is find C1, C2, and pick up on a pattern to find out that recipe. So let's go ahead and go try to find the C first term. So if we just go ahead and write our function, so far we have f of x is equal to, well, just f at a, what we just found for C0. But now we have C1 x minus a plus C2 x minus a squared, and so on. So we have to think to ourselves, well, the term I'm trying to get now is that C1. What could I do to this function to try and isolate that C1 term? If we do the same exact trick we just did, evaluate it at x equals a, well, we're going to wipe everything out of this series. We're going to wipe out this term, this term, this term, if we evaluate at x equals a. So that doesn't seem to be the option we need right now. And this is where we start thinking about what properties do we want these functions to have. And well, you may have recalled that I said our functions need to be differentiable. So let's take a look and see what happens if we differentiate both sides of this expression. Well, if we differentiate the left side, that's just the derivative of whatever function we have. If that function was sine, that's now just the derivative of sine, that's just cosine on that left side. Well, on this right side, what's going to happen when we take the derivative of each term? Well, f evaluated at a, that's a function evaluated as specific x value. So that first term, that's just 0. Because the derivative of any constant is just 0. Let's take a look at what the next term is. Well, if we're taking the derivative of c1 times the quantity x minus a, if we differentiate that, that's just giving us a c1. Let's take a look at the next term. If we differentiate the next term, we do the power rule, we get a 2 times c2 quantity x minus a. If we take the derivative of the next term, we get plus c3 x minus a squared, and so on. Well, now let's take a look at what we have here. Are there any values in which we could evaluate this derivative at that will just give us that c1 term? And well, looks like our trick from before will help us here. If we try evaluating the derivative at x equals a again. So let's do that. If we take our function, our derivative here, and we evaluate it at a, well, every term on that right-hand side is going away except for that c1. For example, we have c1 plus 2 times c2. This will be a minus a when we evaluate at x equals a. Plus 3c3 x minus a squared. Oh, sorry, that's a minus a squared. And so on. So all of those terms, those are just going to 0 because we're getting a minus a's. So the only term that survives is that one that we cared about. So we've picked out our second coefficient. C1 is equal to the derivative of our function evaluated at a. And remember, going into this, a is some number that we're choosing before finding the power series representation. Well, let's do a similar thing to find C2. And while you may have guessed it, instead of starting with the original function and its power series in general, we're going to start off with the derivative line and go from there and sort of repeat the same exact process. Oops, sorry. So finding C2. Again, we're just going to skip right to the first derivative of our general power series, which is C1, which we found to be f prime at a, plus 2C2 x minus a plus 3c3 x minus a squared, and so on. I'm in fact going to write the next term, which is 4 times c4 x minus a cubed. And our goal here is to figure out what this c2 term is, or what the value of that c2 coefficient is. And we can go through the same exact process. If we were to evaluate this derivative at x equals a, well, we're just going to get f prime at a equals f prime of a. So we could try again is that same trick we did just before. You know what? Take a derivative. So instead of the first derivative, take the second derivative now. If we take the second derivative, that's going to wipe out that first term because f prime at a is just some number. It's a derivative explicitly evaluated at some number a. So we get 0 coming from that first term when we take the derivative. Take the derivative of the next term, we get 2 times c2. If we take the derivative of the next term, we'll get 3 times 2 times c3 x minus a to the first power, and then plus that next term, we'll get plus 4 times 3 times c4 x minus a squared, and so on. And well, if we want to try and isolate again this c2 term, we can just evaluate now the second derivative at x equals a. And when we do that, it's going to wipe out the x minus a to the first terms, the x minus a's to the square terms, and all those higher order terms. And what we'll just get will be the following. We'll get f prime, or f double prime, excuse me, evaluated at a equals 2 times c2, because all those other terms are going to 0 when we evaluate at x equals a. And this will just give us, when we solve for c2, that c2 is equal to the second derivative of our function evaluated at a all over 2. And well, we could continue this pattern over and over. In fact, we're going to go out just one more term. And the reason why we're going to do that, you might be curious to think, well, why did I start writing things as 3 times 2's and 4 times 3's instead of just, hey, 6 and 12? Well, we're going to start seeing that factorials are going to come into the mix. Because in this term for 2, when we took the first derivative going to the second derivative, this is really a 2 times a 1 when we take the derivative of x minus a to the first. Well, let's actually start writing stuff out more explicitly. So looking for the third term, c3, we start with our second derivative of our function, which written as a power series, then just looks like, again, just 2c2 plus 3 times 2 c3 x minus a plus 4 times 3 c4 x minus a squared, and so on. And well, if we want to find c3, we're going to take a third derivative and evaluate at x equals a. And when we go ahead and do that, we get the third derivative at a is equal to 3 times 2 times 1 times c3, coming from the derivative of x minus a to the first, plus 4 times 3 times 2 times C4 x minus a, plus all the higher order terms in that. And if we oops, sorry, that's not x minus a, that's actually an a minus a. And when we start evaluating all of those other terms, just like we saw before, those are going to 0 because we're getting a lot of a minus a's. So if we go ahead and solve for C3 from this, we'll find that C3 is equal to the third derivative of our function evaluated at a all over 3 times 2 times 1, which we could write equivalently as the third derivative evaluated at a all over 3 factorial. And in general, we could continue this process, but we're going to skip ahead a lot and say, finding the general nth term, so n could be any value here, what we'll find is the nth coefficient of our power series, or our Taylor series in this case, is the nth derivative of our function evaluated at a, again, where we're centering our Taylor series, all over n factorial. So this is our general recipe for finding Taylor series, or finding the power series of any differentiable function. We take the nth derivative, evaluate at a, where we're centering our power series, divide by that n factorial, and that gives us the coefficient of the nth term. So let's write this out a little more explicitly. So, if a function f of x has a power series representation it has the following form. We can rewrite that differentiable nice function in terms of that infinite power series, where each coefficient on each x term is our function evaluated at the nth, or the nth derivative of our function evaluated at a, where we're centering that power series, all over n factorial times the x minus a term to the nth power. This is the recipe for finding the Taylor series, or the power series, of any differentiable function. So another way to rewrite this, going term by term, is exactly what we just found. This is equal to, well, the 0th derivative of the function, which is just the function itself, over 0 factorial, which is just 1. So that first term is just f of a. The second term is f prime at a, all over 1 factorial, times x minus a to the first power. When n is equal to 2, we take the second derivative of the function evaluated at a, divide by 2 factorial, and multiply by x minus a squared. When n is equal to 3, we take the third derivative, evaluate the third derivative at a, divide by 3 factorial, and multiply by x minus a cubed. The fourth term, you guessed it, we take the fourth derivative, evaluate that derivative at a, and multiply by x minus a to the fourth power. And again, this is an infinite series, so this thing would just go on forever. But hopefully you see that this is now a recipe for finding each coefficient of a power series for a specific function that we care about. So again, to note, when we're trying to find a Taylor series or a power series for any function, what I want us to remember is we know what the function is. So we know f of x. So we can take any derivative of f of x that we want. The first derivative, third derivative, 10th derivative. We know that function. We can think of that like sine or cosine or the exponential. The other thing we get to choose is we get to choose a, where we're centering that power series. And we'll see in the next video, usually for a lot of these types of Taylor series or power series representations, we tend to choose a equals 0. But we'll get into that we'll get into more in that in the next video. So please check it out.